Hi there, welcome back. Today we're going to give an overview of the techniques used in semiconductor manufacturing. My name is Vivek Subramanian.
And I'm Michel Maharbis. Let's get started. So what we want to do is walk you through a very brief, cartoon-like, in a sense, introduction into the technologies that go into building the type of silicon integrated circuits like your processor and your computer. And what we're going to try to do is start from the very basic idea of a wafer, of the silicon substrate onto which we build integrated circuits, all the way to some basic ideas about packaging. There's no way we can cover the vast array of complex methods used in modern fabrication. We're just going to hit some common themes to give you an appreciation for what goes on. So when we say wafer, we mean the thin slice of semiconductor, usually silicon, if we're talking about commercial digital circuits. It's a thin slice of semiconductor material that's very, very polished on its surface, atomically smooth usually. And so here you see a picture of my friend Velko holding such a wafer. This is a 4-inch wafer, and you can see his face reflected in the mirror smooth surface of it. He's holding it with tweezers, and you can see some other stuff that he's holding with his hand sort of reflected. Production wafers are 12 inches usually, so they're much larger than this 4-inch sort of research grade wafer. And
Michel, when you say atomically smooth, that really gets to a key point. These are actually made so smooth that if you were to measure the average roughness across the entire wafer, it's on the order of an angstrom. So it's really, really smooth. It's amazing the precision that goes into making these wafers.
Absolutely. The other cool thing about the wafers is that they're essentially a single crystal of silicon, and so the smoothness in part comes from the fact that you're not quite across the exact same crystal plane over the surface, but pretty close. There's very few step dislocations as you go across. So this is one almost perfect crystal of silicon. Now, a wafer, once it's processed, once we do things to it that we're going to talk about in a minute, it's usually sawed up into die or chips. And these are little square pieces, and that's what some of you think of as the chip, the microchip or the processor chip. And that little square piece will then be packaged in a plastic or ceramic package and plugged into your motherboard and so on. So they're going to be diced up, they're going to be sawed up. We'll talk about that a little bit. Lithography is another term that we're going to use and we're going to define in a minute more carefully, but basically there is a common suite of processes that together are called lithography, and they're really the methods we use to define the patterns on the wafer that will allow us to build transistors and metal interconnects and so on into that wafer.
The way to think about it is the following. What we've started with is just a bare piece of silicon. To create the functionality we want, whether it's resistors or transistors or wires, we need the ability to put different materials in different locations so as to create patterns. Lithography is what allows us to get there.
Exactly. It's a patterning technology or set of technologies. The other term that's useful to know, and you're about to see Vivek use it, is the term photoresist. And photoresist is a term for, again, several families of polymer materials that can be spun on or can be used to coat the wafer to protect it. And the key thing about photoresist is that we can actually put patterns into that polymer material, as you'll see in a second.
Yeah, and specifically what you're going to see is that photoresist is light sensitive. So we're going to use that in our first module where we're going to talk about lithography. So let's talk a little bit about lithography now. What I'm going to do is I'm going to walk you through a series of steps that explains how we create a pattern in photoresist. So let's go ahead and take a bare silicon wafer, and we will drop some photoresist on it. The photoresist, as Michel said, is a polymer. So it's a polymer with a solvent that makes it into this goopy ink-like material. And we'll dispense it onto a silicon wafer. And then we'll spin the silicon wafer at high speed. Typically the speeds we use on the order of a few thousand revolutions per minute. What that does is it causes the photoresist to spread out to form a really uniform layer. And the uniformity is surprisingly good. Considering you're spinning it, the uniformity will be on the order of a few percent across the wafer. And by the uniformity, I'm referring to the thickness of the photoresist. So what we are able to do then is by putting this drop down and then spinning it, we create a thin layer of photoresist, and the process of spinning it also causes all the excess solvent to dry up. What we've therefore got is we've got a dry film of photoresist, Usually after we've got the dry film, we soft bake the photoresist, which means we take this silicon wafer with this coated film on it, and we heat it up to a low temperature, typically somewhere around 100 degrees Celsius. And what that does is that gets rid of residual solvent, and it hardens the resist a little bit to make it usable. So now we're ready to go ahead and make our pattern in it. The way we do that is, for example, using an optical lithography technique. So that's what I show over here. Here's what I do. I take a mask, and the mask is typically made of glass or quartz, and it has regions of chrome on it. So you can see I have a picture of a mask over here where I've got black chrome on the right and black chrome on the left, and in the middle I have an opening. And I hold that above the wafer. In a modern system, I'll actually use multiple lenses as well. And then I shine light through the mask. The light gets blocked in the regions where I have the chrome, but passes through in the regions that have the opening. The result is, if I look at the photoresist under the mask, the regions under the opening receive light. The regions that are blocked by the chrome do not. Now this is where we get to the key property of photoresist. As Michelle said, photoresist is a polymer. And it turns out the light affects the polymer. Depending on the type of photoresist, it can either cause it to cross-link, in other words, form this dense network, or it can break existing cross-links. Anyway, the consequence of that is we've changed the chemical properties such that there's a difference between the photoresist film under the chrome and the photoresist film under the openings. So now what we do is we take this wafer, which has now gone through what we call the exposure process, and we develop it. And what we do in developing is we dunk it into a chemical that will etch out one of the regions but leave the other. So in the example shown here, I dunk it into a chemical that etches out the exposed region but leaves the unexposed regions. And so the consequence is when we're done developing, what we are left with is a pattern that to a large degree mimics the mask. And so you see now that we've got a technique to create patterns in photoresist, and then the next step is going to be to figure out how to use this pattern to create patterns on the wafer.
That's right. Now, one of the cool things about lithography is that the developments in modern lithography are really astounding. And for those of you that like computational electromagnetics and dealing with the wave properties of light and so on and how they interact with chemistry, there's just a very large ecology of people that work on modern systems because the feature sizes of modern systems are on order of the wavelength of the light that we use routinely for this. And so it gets to be a very complicated problem what kind of little aperture you make to get the type of feature you want here. So there's a very nice sort of career path in dealing with the advances in patterning systems for semiconductor processing. So now we've got a way of patterning. What are we going to pattern? What is it we're going to do with this basic way of just putting features down? So we thought we'd show you 3 types of processes that can be carried out on a wafer that are pretty easy to understand. So the first one is implantation or implant. And in this one, what happens is I have a silicon wafer, and the surface of the wafer is my dotted line, and inside I have my silicon atoms. And what I'm going to do is I'm going to accelerate ions of a different type, maybe phosphorus or boron. And when I accelerate them, I'm going to essentially get them by pure kinetic energy embedded some distance into the material. So there's going to be a lot of them at the surface, and they're going to drop off the deeper you go because fewer of them or less of them were able to penetrate that far given some initial amount of energy. Okay? Now, you might ask, well, what is this good for? And of course, without getting into the detailed solid-state physics of semiconductors, we can say that the addition of these types of dopants changes the electrical properties of the semiconductor by changing the amount of positive or negative charge carriers, and it allows us to play games with the devices we can build. And we're going to come back to that in a baby way later. Another one that's also pretty easy to understand is simply deposition. So there are multiple ways of getting atoms and molecules to land on the surface of the wafer in an organized or semi-organized way, such that over time they build up a layer. Okay, for example, a very common thing that is done is called physical vapor deposition, where, let's say, a metal like aluminum is heated up somewhere else, hot enough that effectively it evaporates out, and the wafer is placed nearby so that when these evaporated aluminum atoms contact the colder surface of the wafer, they recondense, and over time they build up a layer. And there's a lot of very interesting physics and even metallurgy in the behavior of these very thin films in terms of mechanical properties and electrical properties and chemical properties. Is a very, very deep field.
So Michel, if I understand the contrast you're trying to make, implantation is putting stuff below the plane of the wafer, so it's driving it inside, and deposition is building up on top.
That's right. That's exactly right. And of course, before moving on, not everything can be deposited and not everything can be implanted. That's where the specialist knows what can be done in terms of what atoms can be put in each, or with each method. And then the last one that's also follows sort of logically from this is etching. And etching, chemical etching is one kind of etching, and that's simply I start out with a wafer. It's got a surface originally at this dashed line, and I immerse it in some chemical, and that chemical will chemically react with the silicon and bind to it and carry it away into solution, slowly eating away at the surface of this. Etching can also happen in a dry or plasma method, and the same thing happens, it just doesn't happen in a liquid. You don't immerse it in a liquid, you just have an ionized area or plasma area with high energy atoms or molecules, and they will react with the surface of the material, say the silicon for example, and essentially carry it away into the gas phase. So these are some three fairly simple modules, and we're going to show you details about all of them in the next few slides, and then we're going to bring it all back together and give you an example of how you can use everything to make a diode, which is a simple nonlinear device.
Okay, so at this point, Michel has talked about some of the basic processes, including ion implantation. So let's use ion implantation now and specifically look at how we would use ion implantation to modify a wafer. As Michel told you, ion implantation is used to add specific species to the wafer, which can be used to alter the conductivity. That is called doping. Okay, so let's go ahead and then see how we would implant into a silicon wafer. So let's consider I have a bare silicon wafer over here, and I expose it to ions, and these might be ions of boron or phosphorus or arsenic, among other examples. What happens is the ions slam into the wafer, and if the ions are fast enough, they don't bounce back. In fact, what happens is they sort of punch through into the interior of the wafer, and they go a certain depth before they stop moving. It turns out as they enter the wafer, they start slowing down, and ultimately they stop. And so what you end up getting is this region in which you've been able to introduce ions. And these ions now are therefore incorporated into the wafer. So the nice thing about ion implantation is it has extremely good control of the dose. In other words, how many ions we end up putting in to a given region of the wafer. And it controls the dose, namely how many ions, and it has pretty good control over how far they go, because it turns out how deep they go into the silicon depends on how energetic the ions were to begin with. There are some disadvantages to ion implantation. In particular, think about what I'm doing. I'm taking these ions and I'm slamming them at a wafer, so it turns out they do damage the wafer a little bit. And so we have to repair it afterwards, and what we do is we heat up the wafer such that it can sort of move itself around and get crystallized again. So now the example I've given you on the left over here is just blanket ion implantation. Let's try to combine it with lithography, and let's see what we can do. So let's consider a case where I've now got an insulator and I've got a silicon wafer, and I'm going to go ahead and do an implant. So I'll do the implant, but now you'll notice something interesting. The insulator, and this could be photoresist by the way, is used to block the ions in this region, but it doesn't block them in the region with the opening. So ions therefore dope this region of the wafer in the opening, but they don't dope over here. So now when I strip the insulator off, so I can heat the wafer up to activate, to repair the damage, and I can strip the insulator off, and now I'm left with a region of the wafer that is doped versus a region that was not.
Now, this region that's doped because of its characteristic shape is often called a well. Is that right?
That's right, and we call it a well for obvious reasons. This looks like a well in a silicon plane.
Some sort of basin. That's right. Now you'll find that making these types of wells is very common when you're working on transistors or diodes. You'll see it in a second. So let's talk about etching. There's a number of variants of etching, and I thought I'd touch on a couple of flavors. So one basic idea behind etching is what's called isotropic etching. And isotropic, as the name would imply, is the same in all directions. And this is a fairly straightforward idea. So let's say I've got a silicon wafer, and I've somehow got a layer of silicon dioxide on the surface. Now, we haven't told you how you put silicon dioxide on the surface. We will in a minute. There's a couple of different methods. But silicon dioxide is what happens when bare silicon interacts with oxygen, and it's basically glass. It's silica glass, and so you get SiO2. Okay, so there'll be a thin layer of this glass on the surface. Now, I'm going to use lithography to make a pattern photoresist. I put a thin film of photoresist. That's the diagonally hatched layer. And I've opened a window using my lithography, just like in the example a few slides ago that Vivek did. Okay, so that's pretty straightforward. But now I can put this into a bath that etches SiO2. And let's say I put it into a chemical that etches SiO2 in all directions with no preference.
Can you give me an example, Michel?
Yeah, actually, the one that everyone loves to bring up because it summons up horror stories is HF, or hydrogen fluoride. And HF is actually a pretty nasty chemical because unlike other acids like, say, sulfuric acid or nitric acid, which when splashed on your skin will burn you and have a very obvious effect, HF is a very, very small molecule, and it tends actually not to irritate your skin except at very high concentrations. And so it's very easy to get HF on your skin if you're not careful. And it would penetrate through and get right down into your bone and really cause you a lot of damage internally. It's a very dangerous chemical.
Right. So what happens is when it hits your bone is when it really starts to hurt, and it starts doing severe skeletal damage.
Yeah. So HF is definitely not something to trifle with, but that's an example. There are other examples. Certainly there are examples of plasma or dry isotropic etching. An example of that is SF6, or sulfur hexafluoride. But anyway, what you see is that it etched away, and since it's the same in all directions, it doesn't just go down. It goes down, but as soon as it goes down a little bit and sees some exposed silicon here on the side, it'll start going under. So it's going to etch like a circle, kind of centered in the middle here, or something circular based on these areas.
I see. So if I understand correctly, because it's etching the same way in all directions, or at the same rate in all directions, it's effectively giving me this hemispherical shape because it's undercutting laterally at roughly the same rate as it's cutting down vertically.
Yeah, that's right. It's exactly right. And then if you get rid of the photoresist or whatever you might have used as your mask, we use photoresist because it's an easy example, you'd be left with something like this, which is an etched region. Now notice, HF doesn't etch silicon, so as soon as it hits the silicon, it stops. It can't do anything there, so it flattens out. And so if you were to wait a long time, this curve would essentially move to the left.
So, right. Michel, one thing you haven't told me, though, is when I discussed the lithography, I told you how to put down and pattern the photoresist. You haven't actually told me how you remove the photoresist. So it looks like you remove the photoresist. How do I do that?
Sure. So usually you remove photoresist with solvents. There's you could put them in acetone, and acetone will chop all this up and dilute it away. There are slightly stronger ones that are used in the semiconductor fab industry that have other advantages, but that's generally what you do.
And the other things, by the way, we should add, it's common to remove them in. So the photoresist is a polymer, so you can etch it in a plasma, and oxygen plasma will eat it up. It burns it. And it turns out the most common way to remove it in the semiconductor industry, just because it leaves very clean surfaces, is to use something called piranha.
You wanted to bring up piranha. That's true.
I did. And what is piranha,
You just
Michel?
like talking about piranha.
I do. Besides the fish, what is piranha?
Right. So piranha, Vivek wants to turn this into a sort of a dangerous lecture. Now, piranha is basically 5 parts sulfuric acid or thereabouts, and 1 part hydrogen peroxide, and it is a nasty, nasty thing. So the peroxide essentially acts as an oxidizer for the sulfuric acid, and if you throw anything in there that looks like a hydrocarbon, it basically begins to bubble and away it goes. We used to, I shouldn't admit this, but we would take little pieces of Kim wipe napkins and throw them into piranha, and they instantly fizzle, turn black, and disappear entirely as the piranha consumes it, which is why it's called piranha. Does that make you happy, Vivek?
There you go. It does.
How'd you bring up piranha? All right.
Yeah, I'm sure you had fellow graduate students whose research didn't work because you used to sit and throw Chem wipes into piranha.
That's probably true, actually. Okay, so let's look at another one, anisotropic etching. So anisotropic etching, as the name implies, will not be the same in all directions. So that means there's probably going to be some preference, some direction in which the etchant works preferentially. We're going to start with the same example. We've got SiO2 or silicon dioxide, and it's got a mask of photoresist. But this time when I add the etchant, it's not going to eat evenly in all directions. Now we've exaggerated this and picked some magical etchant that only goes straight down, leaving SiO2 completely unetched in the lateral directions. This is unlikely. Even the most anisotropic etchants will undercut slightly, but the point is that in a perfect anisotropic etchant, just like a counter to a perfect isotropic etchant, you won't get any undercut. You're only etching in the down direction, so to speak. You can get pretty close to this using an RIE a plasma system, and there what you're doing is you're essentially building a plasma above the wafer and then accelerating the reactant molecules down onto the surface. And although they certainly react in a chemical way, it's this acceleration that gives them the ability to remove layers more aggressively as you work down, sort of in the direction of that the ions are being accelerated, and leave most of the stuff on the sides away. There is quite an interesting industry on how you make very, very anisotropic etchants, but for the moment, this cartoon I think will suffice. And here's an example. We get rid of this, and now you have a very, very straight cut. Okay, fair enough. I think given that we talked about SiO2, I think it's a good place to introduce oxidation.
Sounds like a plan. So as Michel indicated, the basic idea associated with the formation of SiO2 is the fact that you can take silicon, expose it to some sort of oxidizing species such as oxygen, and the silicon will react with the oxygen to form SiO2. SiO2 is glass. You are familiar with SiO2 in the form of glass, sand, quartz. They're just different phases of SiO2, so to speak. But the basic idea is we take silicon, we expose it to oxygen, we form SiO2. It turns out it'll also happen if you expose it to high temperature steam. So if I take silicon and I expose it to steam, I can also form SiO2 as well.
So I'm sure the chemistry is a little different, but it sounds like it's similar to rusting iron.
Yeah, that's right. In fact, that's true. It is. So what happens is we expose the silicon to an oxygen source. The oxygen interacts with the silicon, and it starts forming silicon dioxide. Now, if you think about this, this is kind of interesting. What's happening is the oxygen is actually eating away some of the silicon and consuming it to form SiO2.
Oh, that's right, because it grabs an Si and O2, put it together, makes SiO2.
Correct.
You're left with that, and some of the Si, of course, went into the SiO2.
Right. So what happens is the effective remaining thickness of Si gets smaller as the thickness of SiO2 gets larger. There's also a volume increase, right? Because I've taken something that was just silicon and I've added oxygen. So it turns out the amount of SiO2 you grow is thicker than the amount of silicon you consumed.
So that's why we call this growing and not depositing, because we're not adding a layer to the top of the wafer. We're literally building or growing a layer out of the wafer.
That's exactly right.
Okay.
And as we continue this process, what you find is the SiO2 will get thicker and thicker, and over time you can grow, SiO2 that is microns thick, depending on what you're doing. So that's the basic idea then behind the oxidation process. And we keep going, and now what we're left with by the time we're done is a nice thick uniform layer of SiO2. One of the really nice things about these oxidation processes is they are determined by your gas concentrations, they are determined by the pressure of the overall system, and they are determined by the temperature, and we can control them extremely well.
And I think that's a great point. So there are other methods of putting SiO2 on the surface of a wafer, which I'll touch on one in a minute, or Vivek will, but the important thing is this makes very high quality SiO2. And it's one of the reasons processing is so successful on silicon is that the quality of these insulators is really very good. So, okay, let's look at another method. So now we're experts at oxidation. We thought we'd show you sputtering. So sputtering is pretty neat because it always seemed very violent to me. You have a wafer, and I'd like to put some material on this wafer, let's say gold. And what I'm going to do is I'm going to take a big chunk of the material I want to get on here as a thin film. So I want to get a thin film of gold on here on the surface. I'm going to take a big chunk of that material. I'm going to call it the target. And I'm going to put it some distance away from the substrate, usually, certainly within line of sight, but usually along an axis, right? These things are facing each other along an axis. And then what I'm going to do is I'm going to light a radio frequency plasma that constantly slams argon ions into this target at fairly high energy. And when that happens, as this does that, it's going to dislodge atoms of the target material. It's called sputtering off. And these atoms, in this case gold for my example, will come down and find this substrate and run into it at reasonably high energies, and not high enough to dope, but high enough that they'll smack and then wander around a little bit on the surface, but then they'll cool off, and over time you'll grow a thin film of this material. So in this case, I'm going to grow a thin film of sputtered gold onto my wafer. Easy enough?
Yeah, it's worth pointing out, by the way, that techniques like this are actually used to make the metallized linings of potato chip bags.
I didn't know that. So potato chip bags are sputtered on the inside?
Some of them are sputtered, some are evaporated, but yes.
Oh, that's really cool.
The metallization is actually done that way.
I didn't know that.
So sputtering is actually not that expensive. Okay, so that's one technique for deposition we've talked about. Let's talk about another. So let's talk about chemical vapor deposition, also called CVD. So here the idea is, rather than using a target that we then sputter, let's just bring in the source material in the form of a gas. So here I've got a tube, and I've just put in a bunch of silicon wafers on which I'm trying to deposit a material. And let's say I'm depositing SiO2 as an example. I might bring in silane gas, which is SiH4, and oxygen gas, which is O2, and I'll flow them both into the chamber. The chamber will be hot, and so they'll flow into the chamber. Because the chamber is hot, they'll decompose and react with each other, and then it'll deposit SiO2 on the surface of the wafer. And if I design the chamber right, it'll be pretty uniform across the entire depth. And what I should get is I'll deposit SiO2, and all the residue, which in the silane oxygen example is just a combination of moisture and hydrogen, will come out of the chamber. And so what this allows us to do then is it allows us to deposit as opposed to grow. And so we can deposit films, the uniformity can be pretty good, and we can put 100 wafers into this chamber at a time and deposit them all. So this is called chemical vapor deposition, therefore, for obvious reasons. It's based on a vapor process, and it's based on chemistry that achieves this deposition. So what determines the methodology behind this? Well, it's affected by the pressure. It's affected by the temperature. The higher the temperature, typically the higher the deposition rate. Similarly, generally, as you increase the pressure, the higher the deposition rate. And the gas flow. And the gas flow is kind of a useful knob, because not only does the gas flow affect the deposition, but we can use it to change the chemistry or the stoichiometry. So let's say I'm flowing silane and germane, two gases, SiH4 and GeH4. By changing the ratios of SiH4 and GeH4, what I deposit might be silicon, it might be germanium, or it might be silicon germanium, where by changing the gas flows, I can control what actually is deposited.
So the key here is that you've got the reactants, and they're going to become products on the surface of the wafer. And just like any chemical reaction, you can control the parameters by controlling pressure, temperature, flow, and so on, just like in chemistry.
That's right, except we're doing it on the surface of a silicon wafer.
How big how many wafers can you do at a time in one of these tubes?
Well, it depends on the tube. So it turns out in some modern tube systems, you'll see as many as 200 wafers. Wow. But there is a trade-off. We actually kind of done a fairly realistic picture here. You see how there's more looks like more reactant species in the front than there are at the rear.
Sure.
That's actually true. That really does happen, especially if you do it like this, where you inject from one side and exhaust from the other.
You're just eating up all the stuff. By the time you get to the end, if you were to do it this way, the last few wafers probably wouldn't look the same as the first few.
Right, so you'll have non-uniformity across your system. So there tends to be limits to how many wafers you can stick in. Okay, so having talked about this, now let's go into let's look at a slightly more realistic reactor. What we're going to do is, as you see, we grow this layer. Let's look at that in a real reactor. Michelle, maybe you can walk through a so-called LPCVD system.
Sure. So this is really identical almost to what we showed you in the slide before. We just thought we'd show you the different components and emphasize the sort of LP part of this. So here you have a tube. This is very similar to the enclosure we showed you before. And on this tube will be something called a boat. And you will load your wafers standing up and down on this boat, as Vivek said. And we have a gas control system, and here are our source gases. We will have mass flow controllers, or essentially little devices that can control exactly how much volume of material, of gas, blows through per unit time.
So that's what's used to set the ratios?
Yeah, the ratios and the rate of flow, both. And so you will bring these in, mix them up, and that will be pumped into the system. And as we showed you before, you'll basically get the exhaust moves through some sort of trap to catch anything you don't really want going into the pump, and then you basically have this thing that can pump out. Now here's the key. In many cases, we want to have this reaction happen at pressures lower than 1 atmosphere. And so what we do is we lower the overall pressure in here while changing these flows so that effectively the partial pressure or the fraction of each type of gas in here is also controlled.
So it's worth pointing out why we do that. The reason we run at low pressures is really two things. One is it turns out if you run at low pressures, all the reactions slow down, so it's easier to get uniformity. So that's kind of a nice reason to run at low pressure. You can get more uniform deposition just because everything slows down, so you don't eat up all the gas up at the front.
That's right.
And then the second reason to run at low pressures is if you run at low pressures, you can often get, because the films go down more smoothly, you can actually improve the quality of the film that's deposited.
Yeah, that's right. And this gets to, both of those points gets to a common theme that we touch on from time to time, which is really the beauty of modern semiconductor fabrication processes. We're really talking about atomic control over the deposition, and that's exactly what this lets you do. It lets you go slow enough that you get very, very nice uniformity and very, very slow growth, so you can control it down to the nanometer or below in some cases. So that's a simple LPCVD system. Now, we haven't yet we haven't yet worked through a process for, say, something like a diode, but we will. But so far, we've really been talking about things we do to the wafer itself, or right around the wafer. And another very important thing to talk about is once we're done building our transistors, there's really quite a forest of wiring on top of the transistors that's often multiple levels of metals.
That's right. In fact, if you look at modern processors, you can have 6 to 10, in some cases even more, layers of metal above the transistors. And think of these as local roads and highways that are used to connect the transistors together to form a circuit. You'll remember previously we talked about devices versus circuits versus systems. Well, what allows devices to become circuits is the interconnects,
right,
which we then use. And the interconnects are all formed using the same deposition and etching techniques that we've been discussing already. It's just now these are done to create layers of metal. So this picture over here is kind of an interesting picture. This picture is a so-called scanning electron micrograph, which is a very high-resolution microscope that allows us to take a picture of the wafer. And what they did was, in this particular example, they created all the metallization using a series of deposition and patterning steps where we had SiO2 and metal deposited and etched and deposited and etched and deposited and etched to create these shapes. And then once they were done, they etched out all the SiO2 so you could see what it looked like underneath.
And that part's not normally done. That's really if you get the pretty picture.
Right, this is to get the pretty picture, but it is kind of cool. You can see how complex these are. You'll often hear that of all the things we manufacture, modern integrated circuits have complexity that far exceeds the complexity of a city planner.
Absolutely. I mean, this is what's cool about the integrated circuit. You're going to get on your wafer. You're going to manufacture your transistors, and again, as I've said a number of times, we're going to show you a baby version of the process in a minute. But after you do this, you then also manufacture all the wires at the same time. You manufacture all the patterns that will short all of your transistors, make all the wire connections you need. Think about your breadboard. You put in your resistors and transistors and little packages, and then you sit there with the wires and kind of connect them one by one. This will drop connections for hundreds of millions of transistors all at the same time at multiple levels with sort of hierarchical design choices. Pretty neat, pretty neat. So once this is all done, once we make our chips, there's another whole industrial commercial ecology in how you test them. And we're not going to touch on all of these one by one. It would take longer than we'd like to devote to this. But what I did want to point out is that there's a number of companies. ForFactor happens to be one of them, and this just shows some equipment they use that perform a variety of tests, both on the die, on the wafer, and on the die. And then after the die are packaged, and we're going to talk about packaging in a minute, they perform tests on the packaged devices. And all sorts of tests to go on and final adjustments. It's a really, really pretty interesting ecology of businesses that do this kind of stuff.
So, and just to give you some ideas of some of the testing that we do. For example, one of the tests is a fail fail or pass test, a go no go test, where you'll test your chips to make sure they work, because you don't want to ship a dead chip to a customer.
Of course.
So that's one. But there's other tests as well. So for example, you know that when a new microprocessor comes out, it often is available in 2 speeds. And those are often the identical processor. It's just the company in question is selling them at 2 different speeds. What they do is they test them, and they figure out, well, this particular chip can run at a higher frequency than the other one, so I'm going to sell them at 2 different speeds for different costs.
So what you're saying is that slight process variations will produce a whole sort of normal distribution of performance, and some of these companies will bin them. And is that why when I go to, say, Newegg, I see that similar processors or have slightly different prices? Is that why that happens?
That's right. It is.
That's pretty cool. The other thing I wanted to point out about this is what's really neat for those of you that like very high-end design is the testing instrumentation for the next generation of machines has to, of course, be somewhat faster than the thing you're testing. And so you're pushing the envelope when you're working on all the test hardware.
Yeah, and think about this. Take a modern microprocessor. It has 1 billion transistors and executes hundreds of instructions. Think how long it takes to test to make sure that all of those transistors work and that they execute all of those instructions correctly. Testing is a really big deal.
Oh yeah, makes people a lot of money, that's for sure. All right. So packaging, we haven't really covered what happens to the die. How does it go from a little silicon die to the, I guess, black square or rectangular enclosures that most people conveniently call a chip when they see it sitting on their motherboard? There's lots of different ways, and so let's touch on just a couple in 2 different slides. The oldest traditional thing that happens when you want to go from a die to a package, and a package is the thing into which you're going to place the die, and that's what's going to bond onto your printed circuit board. And Vivek's going to touch on that in a minute a little bit more. But inside, going from the die to the internals of the package are these little tiny wires, and this is called wire bonding. And so there are machines that will bond one end of a tiny wire, tens of microns in diameter, down to one of the little pieces of metal on the silicon. They're called pads. They're the ends of interconnect. So here's an example of one. And they'll bring this wire down and apply a combination of pressure, heat, and ultrasonic energy to bond on a stubby end of it. And then it'll guide the remainder of the wire in a loop, sometimes a very tight loop. You see multiple pictures. Each of these little lines here and here and here, and then down here you see all these lines. These are all little wires. They go from one end, and then it brings it down to where on the package you want to bond the other end, and it'll perform a similar function and then break it off. And these are blindingly fast. Modern automated wire bonders can be programmed to do the same thing over and over and over using visual recognition of the die, and they're so fast you can barely see it. It's faster than a sewing machine. This thing is just flying across the die, wiring it. This is how you go from this very complex die. Notice if you look in the center of this die, you can see what looks to be lots of up and down and left right looking spaghetti. That's all the interconnect. That's the sort of what it looks like in white light, all the metal interconnect. And this is the very complex digital circuit. And then at the periphery you have these pads that then talk to the outside world or the package. Now what does the package look like? Well, it looks like a lot of different things.
That's right. So the package is actually the outer surrounding on the chip, and it encapsulates the chip itself as well as the various package interconnections that we talked about before. So Michelle already pointed out that there can be wire bonds on the inside that go from the chip to the outer substrate. There are other types of packages that exist as well. So for example, this is a ball grid array where rather than using wire bond, the chip is actually flipped over and little balls of solder are placed between the chip and the substrate to make connections. Then the whole thing is put inside some sort of protective case, typically some sort of epoxy or black plastic, and that's what we buy when we buy chips. And what has that given us, all said and done? It's taken the die and it's given us a way that we can now have a mechanically robust system that we can then attach to a printed circuit board. And so that's basically what packaging is.
Yeah, and there's lots of different flavors, and you can learn about them, as your interest dictates.
Okay, so having done that, I think it's now time to put this all together and let's work through an example. And the example we're going to work through is a very simple device fabrication process. So we'll walk step by step together, and I'm going to start by taking a silicon wafer, and PSI just means a P-type silicon wafer. Don't worry about what that means if you don't know, but it's basically a bare silicon silicon wafer, and we're going to go ahead and start to make a device in that. So the first step I'm going to do, step one, is I'm going to oxidize this wafer. So I'm going to take this wafer, I'm going to stick it into oxygen or steam to grow oxide. You'll notice, Michelle, that there's oxide on both sides.
Oh yeah, that's right, and we didn't emphasize that in the previous slide. So anywhere that the wafer, any part of the exposed wafer that sees steam or if it was dry oxygen, but steam is going to oxidize. So it doesn't matter if we don't really care about the backside, as long as there's silicon exposed, it'll oxidize. And we haven't really drawn this part here, but this would oxidize too. It's just where we're sort of saying we're looking at a region of the wafer, just a chunk of it. If we were to extend this all out and say, well, this was the actual end of the wafer, then that would have oxidized too. Any exposed silicon oxidizes. Okay? So now we're going to do a lithography step. Spin photoresist, and we're going to place our mask with our chrome regions that are going to block light. We're going to shine UV onto that photoresist, and we're going to then, after we expose it, we're going to leave behind a little bit of photoresist that's not there. Okay, we're going to follow all of the lithographic steps of that previous slide. So we're going to be left with photoresist here and here. Okay, and get rid of the mask. And then what we're going to do is use that photoresist as a protectant for etching away the silicon. Remember, we covered the silicon dioxide. Remember, we covered that in another slide. The photoresist will protect all the regions we don't want etched of silicon dioxide, but wherever we exposed and the photoresist was removed in this region, that area will get etched in the etchant. And so we'll be left with silicon dioxide everywhere but that little window.
So looking at this, it looks like you performed anisotropic etching here, and I'm saying that because these lines appear to be pretty straight.
Yeah, that's okay to assume that for this example.
Okay, all right, great. So now we've gone through a lithography and etch step. Let's go ahead and proceed to use this oxide window. In other words, I've got an opening in the oxide to act as a mask for implantation. So I'll perform arsenic implantation, and I will implant arsenic, and I'll count on the fact that the SiO2 is thick enough to block the arsenic from getting into the wafer in the regions where the SiO2 is present. So what's going to happen is I will implant arsenic, and arsenic turns out to be an N-type dopant. So it's going to create some N-type material in the silicon wafer right around the opening. When I heat it up, the arsenic will spread a little bit. So besides the damage being repaired, there'll also be a little bit of spreading. And so what I end up getting is a little bit of encroachment of the N-type region under the window.
That's clever. So basically the silicon dioxide is used essentially as a window or a stencil for how you dope it.
That's cool. Right. That's right. So what we've done now is we've essentially created a localized N-type region in a P-type wafer. And now, maybe, Michelle, you can talk about the next step, which is putting down the metal.
Yeah, so that part's pretty easy. What we're going to do is we're going to take our wafer that's right here. This is just a section of it, but here's the wafer. We're going to put it into that sputtering system we described to you. In this case, we're going to sputter aluminum. So we're going to accelerate argon into the aluminum target. The aluminum atoms are going to blow off the target, and they will redeposit onto this wafer, and they'll just do it everywhere. So you'll notice it'll make a thin film, which will follow the topography of the underlying wafer, and wherever there's a step, of course, it's not going to go perfectly. It's just going to sort of follow it in a smooth, sort of continuous way. Now, once we've got the aluminum there, we don't want aluminum everywhere. This isn't the inside of a potato chip bag. So what we're going to want to do is add patterns to the aluminum. We're going to want to remove aluminum where we don't want it. So all we're going to do is do another lithography step. Here we've got resist and a mask through which we're going to apply UV. Okay? So want to take it from there?
Sure. So because we used that mask, we were able to get photoresist in the regions we wanted. We can then etch the metal, just like we etched the SiO2 earlier. And so what we're left with is a patterned metal. So in other words, we're now able to make a contact to the device right where we need it. And then after that, we can deposit a layer of silicon nitride as an example, which will be deposited by chemical vapor deposition to cover the entire thing.
And that's an insulator, right?
That silicon nitride is an insulator, and it turns out it's also a very mechanically robust insulator. So we use it to protect the device.
Ah, okay.
So it forms a protective cap layer. But now, of course, the problem is, as I've done it right here, it's covering the entire device. I don't really have access to the device anymore. So what I then do is I perform another lithography step to open up a window, and that creates this little pad. And of course, what do you think I do with this pad over here, Michelle?
My guess is you're going to wire bond to it.
That's right. So what I'm going to do is I'm going to use this for putting into a package. But now there's an important step. You remember when we did the oxidation and there was a bunch of oxide on the backside? I need to clean that up.
So you're gonna sand the bottom.
Right. So what I do is I protect the front side, typically with photoresist, just so that it's saved while I'm flipping the wafer over to clean the backside.
Right. So you don't scratch it or whatever.
Exactly. And then I'll clean up the backside by, we call it backside milling. Typically that's actually mechanically done. You just polish it to clean it up. And then, so that you have access to the backside of the wafer, you might deposit some metal in the backside. That gives you a good contact to the backside of the wafer. So if you think about it, what do I have now, Michelle? I've got a backside metal, and I have a front side metal with a contact window opening.
Well, my guess is now we've got to make electrical connections. I guessed we were going to make an interconnect here, but I had forgotten that the back was oxidized. We had to clean it, and then we had to put a metal to make a good contact. So there we go. So now what I'm going to do is take this chip that's completed, I lay it onto a printed circuit board with a metallized pad on the bottom, and then I run a wire bond from the top to the bottom, and now I have my two contacts. Here are my two leads, and I have a diode. Now, there's lots of cool things about this. I mean, this is a very simple process. We didn't use it to make a transistor. We used it to make a simple diode. But notice how using the aluminum etchant, we could basically draw a wire wherever we wanted to. Now imagine that after we cut this window, instead of wire bonding, we added another metal layer and etched that one, and then added more nitride and cut a window, and then another metal layer. You could build up a whole series of floors, essentially, of wiring that crisscrosses each other, as in that SEM. But the net effect is, if you can follow the description we just gave you, you pretty much know how to build a simple diode. This could be a light-emitting diode or a rectifying diode. It could be all sorts of things.
That's right. And in fact, going a step further, you take these steps and you multiply by several tens or a couple of hundreds, and you end up with the processes that are used to make modern microprocessors. I mean, there's significantly more complexity involved, but basically it's this idea repeated over and over.
Pretty cool. I hope you enjoyed it. I hope you guys learned something, and we'll catch you in the next one.
Take care.